Hey guys, thanks for watching this video. It's the last week of class, and so we need to talk about chapter 11 and 12. We talked a little bit about 11, but these videos are going to count as a review and studying the chapter. We're kind of running out of time, so we've got to be efficient with the time that we have. Okay, so the videos that I'm going to do are very relevant for the test. So I strongly recommend you watching these videos. Let's get to the first problem. We're going to look at the problems, and as we look at the problems, we're going to use those as a way to understand the physics. So when we do a problem, I'm going to explain the physics of how that problem works and how to find the solution to it. And we'll try to make it as efficient as possible. First problem we're going to work on today. James Joule, after whom the unit of energy is named, claimed that the water at the bottom of Niagara Falls should be warmer than the water at the top, 51 meters above the bottom. He reasoned that falling water would transform its gravitational potential energy at the top into thermal energy at the bottom, where the turbulence bring the water almost to a halt. Okay, so if the transformation is the only process occurring, how much warmer will the water at the bottom be? Okay, and then the specific heat is 4,190 joules per kilogram per Kelvin. Okay, so we need to talk about what specific heat is first of all. Okay, so I'm going to look at the chapter and the book for some of these explanations because the book is really good. Okay, so this is section 12.5 of the book, and we're going to be talking about specific heat. Okay, um, and at first they start talking about basically if you're holding a glass of ice water. I've got a glass right here. Okay, as I hold this cup of water, energy from my body is going to flow into the water, right? And this is why it feels cold. If something feels cold, that means that thermal energy from your hand is going into this object, okay? If it feels hot, that means that energy is flowing from that object. So that was my water. So I've got my hot coffee here. See, I'm living thermodynamics, but this is hot coffee, right? The human body is amazing because we can sense which way temperature flows. This is obviously important for survival because you needed to know if you're freezing to death. And so people that could measure temperature obviously survived longer because they didn't freeze to death. Okay. Um, hmm. And eventually, you can melt ice. Okay. So if I put this piece of ice in my mouth, I'm not going to actually do it long enough, but go get a piece of ice from the refrigerator, put it in your mouth, and see how long it takes you to melt that ice. Okay. When you're doing that, the energy that is in your body, in your mouth, is changing the form of that solid. Okay. And when you go from a solid into a liquid, that takes energy. That energy comes from you, or maybe it comes from the air if you just leave it out on the floor. Sometimes my ice machine drops ice cubes on the ground and I don't pick them up, and then people yell at me. They say, "Why didn't you pick up the water, the ice?" I didn't see it, but that energy from the air molecules goes into heating up the ice and changing it. Into a different form. Okay. And we're going to talk about that because that takes energy. That's called the energy of transformation. If you go from a solid to a liquid, that takes energy. Or if you go from a solid to a gas, that also takes energy. Okay. And if you heat something up, okay, it takes a certain amount of energy to to raise the temperature of water. Okay, so if you're like me and you like coffee and tea, um, I need to supply a certain amount of energy to get that water to boil. Okay, so and as I apply water, or sorry, as I apply energy, I'm transferring heat, right? Heat is the flow of energy, right? So as I'm putting heat into the water, the temperature of the water starts to increase. Now, what happens to the molecules? Well, as in a liquid or a gas, as they gain more thermal energy, what that means is that they have higher kinetic energy. So, if you're in a room and it's very hot, the molecules in that room are moving much faster. Okay, same thing in a liquid. If you have a liquid, and you bring it close to boiling, those molecules are moving very fast. Okay, so thermal energy in a solid or a gas, it can, especially liquids and gas, that means they have higher kinetic energy. In a solid, if when things can't move around, there's still kinetic energy there, but then it's in the form of vibrations. Okay, so that means the atoms are vibrating more quickly. But it takes energy. And so, getting back to our problem, we want to know how much energy or how much does the temperature raise um, in our water when it falls off of Niagara Falls. Okay. But let's go down here to specific heat. Now, for water, the specific heat is 4,190 joules. Okay. Each element, each material has its own unique specific heat. For example, water is 4,190 joules, but uh, 1 kilogram of gold only takes 129 joules to raise it by 1 Kelvin. So this is the amount of energy that you'd have to add to 1 kilogram of water to raise it 1 Kelvin. Okay, and a Kelvin, if you don't know what a Kelvin is, 1 Kelvin equals 1 degree Celsius. So if you raise the temperature by 1 Kelvin, you raise it by 1 degree Celsius. And so the Celsius scale and the Fahrenheit scale are a little bit different. There's a formula that you can use to convert temperatures, but we'll talk about that later. Okay. It's not a direct conversion. Okay, so you have to use a formula. If you know what the temperature is in Celsius, you can convert it into the correct temperature in Fahrenheit. Okay, so here's our formula that we're going to use. Heat needed to produce a temperature change of delta T for a mass M of specific heat C. All right, so I'm gonna write this down now. All right, this is gonna be unimportant equation, and since I'm making a video of this problem, it's probably gonna be on the test. I'm not gonna lie. So make sure you write this down on your card. Okay, so we have Q is going to equal M times C times T. And C is our heat capacity here. And we can look on our table here, and it should have water. Okay, water C equals 4,190. It's got these funky units. Joules per kilogram per Kelvin. Okay, and this is liquid water. Liquid water. Now, solid water, or as some people call it, ice, right? Then C equals 2,900, or we'll call this water ice. Yeah, there's other kinds of ice too. You can have um, ice made out of methane, or all kinds of different things can have ice. Yeah. Okay, that's from the table there in let's see, on page 414 of your textbook. Okay. But this is the formula we're going to use here. And T, well, that should be we'll call that delta T times C times M equals Q. Okay, and delta T here, temperature change. Temperature change is delta T. How many Kelvin did this thing change, right? Or how many degrees Celsius? Um, Now M is our mass, so mass obviously is M, okay? And then Q is um heat or energy, yeah, energy transferred. All right, now in this problem, okay, so here let's draw a picture of Niagara Falls, okay? So and there's just an absolutely tremendous amount of water coming down Niagara Falls every second, okay? And so, people like to use waterfalls to make hydroelectric dams because you can take all of this energy here that comes from the water and you can convert it into electricity, right? If you know how much energy you have here, okay, then think about how much electricity you could make. The great thing about hydroelectric energy is there's no carbon produced and there's no nuclear waste, okay? Y- do you destroy a pristine natural habitat? Yeah, you kind of do, but you got to get electricity somehow. All right, so the question in this problem is, right, we know that the water is falling 51 51 meters. Okay. Water's falling 51 meters. Um, so how much energy are we going to get from this? All right. Now, one thing that's I found really glaring, the first thing that jumped to my mind, right, if I don't really think about it too much, is right, in our problem here, it never mentions the mass. We don't actually know um how much water is coming down here. Okay, we could look it up. Okay, and I think it says somewhere else in the book there's another problem where it actually tells you how many millions of gallons of water are coming off of this thing. Okay, but it that really jumps out at me in the beginning is it doesn't tell us the mass of the water. Okay, and so in terms of solving this problem. Okay, the energy change or potential energy change is this going to be M times G times H. And you're like, but Dr. Wisby doesn't tell us M. I know, but remember that they wouldn't give you a problem that you can't solve with the information given, okay? And so, spoiler alert, mass is probably going to cancel, okay? That's just, if they don't give you a mass or some important variable, it's probably because you don't need it. Because if you set it up symbolically, then you're not going to need to worry about it, honestly. Okay. So basically, what I'm saying is, right now, conservation of energy is always true. Conservation of energy still works. And we're going to we talked in chapter 11 about that. I'm going to make some more videos about that actually. But, if you have some process, that energy doesn't go away. So if you have a waterfall, where does our energy go? Well, it starts off as potential, and then down here, our energy ends up as thermal energy. Okay? It doesn't have anywhere else to go because the water basically stops. That's what it says. So it has to lose this energy somewhere, right? We start off with potential up here, right? So up here, all the energy in the water is potential. This is why people build dams because there's so much water here and you can make so much electricity. All this energy just it's constantly flowing and just through natural processes, right? Rain and evaporation it refills itself. So you just have this huge amount of energy that's supplied to us by nature. Okay. So then we can say U equals our thermal energy here. And so U is going to become Q in this problem. So we're going to say U equals Q. So the potential energy equals the heat flowing into our water. All right, so let's plug these two things in. So we have mg times h, okay? And then over here on this side we have mc times delta t. So it turns out the mass doesn't matter. Okay? It really it just cancels out. I know it seems weird, but it really doesn't matter. The only thing that matters is the height of the waterfall. Okay? And this is how much heat is going to be released. Okay? So delta T here. And let's go back and read the problem carefully. Okay. Well, it just says how much warmer? Well, let me share my screen here. Okay, it just says how much warmer will the wa water be at the bottom, right? If we know all the water at the top has a certain temperature, then it's going to be warmer at the bottom. How much warmer will it be? Well, let's calculate it here. We're going to solve for delta T. I'm going to get everything over here. So I will have G times H over C. Okay. Um, and so that's going to give us 9.81 meters per second squared uh, times 51 meters. That's the height of Niagara Falls. And then we looked up the heat capacity of water, 4,190 joules. All right. So when I plug in the numbers here, okay, I get 0.19 times, yeah, 0.119. Let's check it out and see if we got the right thing. Seems really weird that we have mass in the constant here, and we should have kilograms. So this kind of makes sense. Okay. Okay, I get it now. So this is actually Kelvin per kilogram. All right. So the correct answer is delta T is going to equal 0.12 Kelvin, and the answer is in Kelvin. All right, the last thing we need to deal with this problem is we need to deal with the units because that really is an important point here. And in the denominator here, we had joules, okay? And here we have kilograms per Kelvin. So we can't just ignore those units. We need to actually deal with the units here. So we're going to put the units back in. All right, we know what the numerical answer is. That's correct, but we have to figure out how we get to Kelvin. All right, here we go. All right, so joule, all right, we know that this is equal to 0.12, okay? And then let's go through and actually work with the units here. So we have meters per second squared. Then over here we had meters. And then in the denominator we have joules per kilogram per Kelvin. And since these are in the denominator, they're going to go up into the numerator, and I'll show you how to do that. Okay, so we're going to multiply the top and the bottom by kilograms times Kelvin. Okay, so that's going to cancel these ones. So these come up here into the numerator. All right, now we've got 0.12. We've got meters squared per second squared. All this stuff should cancel because we want to end up with Kelvin. But we need to deal with the joules down here in order for that to happen. Okay, so in the denominator, now we have joules, and up here we have kilograms. That's still left over here. All right, so what are we going to do with this? Well, we need to talk about what a joule is, and one joule, okay, is going to equal, because it has units of energy. So it is kilograms times meters per second squared. And then since it's work, we have another meters here. Okay, so that means that all of this stuff is going to cancel up here. And we also had a Kelvin in there. So we don't want to forget that. All right, so let's go down here. We're going to put everything in. So first we had 0.12. We know that's the correct answer. Here we have meters squared per second squared. Then we had a kilogram up here times Kelvin. And now we're going to substitute in for joules down here. And so we're going to have 1 times kilograms per meter squared per second squared. Okay, so this is actually, everything is going to work out correctly, and we end up with the correct unit. So let's cancel this out. We have kilograms are going to cancel, meters squared are canceling, seconds squared are canceling, and we have our Kelvin. Okay, so our final answer is going to be 0.12 Kelvin. That is the temperature difference between the top and the bottom of the waterfall. Okay, so it is going to heat up the water a little bit because all of this potential energy gets converted into thermal energy, which means the temperature of the water is going to increase. And this is problem 12.8, 12.89. All right, so there is the whole thing. Problem 12.89, we get our final answer here, and then we got all of the units and everything. Definitely know this for the test. I'd say that there will be a problem like this on the test.
Thank you, like and subscribe down below.